future tree species modeling, assuming some climate changes and projections. Please, Carmelo, 20 minutes.
Yeah, sure. Let's see. Okay. Yeah. Hi, everyone. Thanks for joining. So as Tom introduced, this will be the topic of our discussion. This is a bit of the outline of the presentation, so you have an idea of where we're going to focus on. So the rationale, as I said, is basically mostly because of this task inside the group and the whole consortium. The project that we are going to show is the third component. The first two were presented in the previous global workshops. This feeds the EU Reforestation Planner tool and the two use cases associated to the task itself that you see here on the left. So the point data that we use to produce these maps is an integrated dataset of the EU forest dataset that was published many years ago by the JRC. And then we integrated some the countries existing inside this dataset with publicly available NFIs. So while the source is NFIs for both datasets, there are additional tree surveys or years that were not included in the dataset from Maori. And on top of that, you have more species in the individual inventory from the countries. So we noticed that from the EU forest dataset, you get to approximately 60 species total with integration of additional countries, especially the Mediterranean ones. You manage to have enough data to model up to 90 and more species. The distribution of the data is quite regular. So we have here the centroid of the 1 kilometer inspired grid cells. We include all the trees that are alive from the year 2000. And we include only those species that have at least more than 200 individuals alive across the whole sampling grid. So for the climatic data, this has to be reprocessed during the project, so it's not data that is currently available online. You would have to do all the reprocessing yourself. So except for this historical baseline, which is the one that you can download from the CHELSA project, it has been used for the baseline, the training of the model. We use the historical baseline a period of 26 years. We use only the bioclimatic variables to train the model from a climatic perspective. And this historical baseline has been used to correct the historical run of 6 diverse global circulation model and paired with its additional regional circulation model from the Eurocordex project. We do have predictions on in the future scenarios for the RCP scenario 4.5 or 8.5 on a decadal time step. So we cover the whole period from 2030 to 2100 with one map every 10 years. The choice of this global circulation model and regional circulation models comes from a trade-off between the correlation, because all of these models produced by the IPCC are more or less correlated. We try to get the one that cover different extents in terms of assumption and which kind of tendency. So models are behave much better in colder temperature, other ones are more drier, and so on. So we try to compensate all the global circulation models with the regional circulation models from Cordex that are specifically adapted to European condition. In this case, we added also topography. We tried to keep the model simple because we wanted to see how only climate affects the envelope of the species. So we didn't complicate things further by adding, for example, soil properties or lithology and so on. So we talked about 92 species total. So in reality, we have basically 92 different classification problems based on a 0-1 basis. So it's a binary classification problem. The idea is that in all the points that I was showing before, we have 3 plot level data. So in this case, we consider each plot as a presence for a certain species if you have at least one individual tree measured in that plot. And you can see that it's a serious imbalance data set because basically we have maybe 5 species total that across the whole 300,000 points across Europe cover more than 10% of the whole data set, while most of the species are considered quite rare. So in this case, we could not model each species in the same way, and we have to use a mixture of either weighting based on its prevalence or oversampling, where the oversampling of each point is used only to give false stability during cross-validation and not to change the prior of the world conditions of how the plots are distributed. So this is how we use, like, basically from machine learning literature for binary classification problems, the imbalance in the data set comes if your one positive class is below 10% of the whole data set. So we consider modeling all those species that have more than 10% with no weights and no oversampling. Then below 5%, we included some weights. And then below even that, for like species that are even rarer, so even less than 1% of the whole European continent, you add oversampling just to duplicate the observations without, as I said, changing the prior of the world conditions. This is how the weighting function is applied. So as you see, above 10%, there's no additional weighting, and then the weight increase for each observation based on the prevalence inside the dataset. The gamma in this function is considered as 0.7, so it's a little bit more smooth. It's not 1, so it's not the classical inverse balancing that you would see in normal weighting approaches, while the oversampling basically uses a duplication factor capped at 20, but since the prevalence minimum that we have is 0.1, we don't get above 10, so each observation is duplicated up to 10 times, and this duplication happens until you reach a minimum of 2% of the whole data set. So this is how the modeling pipeline works. Once you have the classification matrix, we do a 80-20 split. We keep the 0-1 proportion as original in both data sets. We use Pearson correlation to filter the covariates, and usually it's around 20-25 covariates total for each model. Then we use 5 different models, and of these 5, 4 needs to be fine-tuned because random forest generally is quite non-sensitive to hyperparameter tuning, so we use mostly default parameters. We know this didn't change that much. We use a 10-fold spatial cross-validation where each block is considered as a 1 kilometer block. So consider that we have 1 point every square kilometer is roughly, if the area is only forested, like around 10,000 points per block. If the prevalence of the species is below the threshold that we talked about before, we add weighting and eventually oversampling. Then we train these 5 models 3 times, so with a 3 cross-validation. Then the out-of-fold of these predictions are used to fit a meta-learner, so logistic regression. And on the final stacked model, we do 2 things. First, we predict on the final holdout of the dataset, and we get some raw probabilities of the model. And we use the final stack model from before to do a 10-fold spatial cross-validation additionally. And the out-of-fold prediction of this model are used to fit a beta calibration function. So this function is then fitted on the raw probabilities, and you finally have calibrated probability predictions. And you will see what does that mean. So in this case, probability calibration is something that we can do only because all the domain that we are mapping is covered, both spatially and from a feature space perspective. So what happens is that if you do have the chance to have the whole domain sampled, what you have in your data set kind of respects and represents what are the real world conditions. So in this case, if you use only the raw probabilities of your model, it can happen that your model can be overconfident or underconfident. In this case, shown in figure, this model is extremely overconfident. So all the predictions that you would have pixel values that can reach even 90, but this 90, it's not a 90% suitability, it's just a ranking of the model. So you do use this calibration function to fix and match the log likelihood of the original data set that you have trained the model upon. So this calibration function is just an isotonic scaling of the final probability. So the area under the curve used to validate the normal SDM models is untouched. And we tested different calibration functions, and we ended up using a beta calibration in this case. But there are also other isotonic functions, plot scaling, and so on. Here we see the Breyer score, which is one of the most common metrics used for probability problem performances. And in this case, contrary to other metric, the lower the Breyer score, the better the model is. So you see that this calibration doesn't help that much with species that have a distribution that is above a certain threshold. So in this case, no weights and oversampling, so more than 10% of the data set. But it helps tremendously when you have very rare species. So it actually helps you to be less overconfident with your predictions for rare species. And the same, we can see it also in log loss, which is another metric used for probability estimation. So here we see one of these 5 species that are not that are basically common in Europe. We see that on the header it's not well seen, but this is like the sessile oak. And you see here on the left the raw probabilities of the model, and this is after the calibration. So you see that basically the maximum pixel value gets smoothed because the model is overconfident, and the metric also gets lower, so your model gets more accurate. And this may not look like that much here, but it also makes things more important. So you see that the log loss and the bar score drop considerably when you consider species that are much rarer, like the maritime pine in this case. So another thing that we need to do is that we need to evaluate these products not from a probabilistic perspective, but also on a hard classes perspective. So because decision makers mostly require binary maps, they want to know what is one thing and what is not. And in this case, for the reforestation planner, the idea is which pixel is suitable to plant the species, which one is not. And you can see that for this kind of classification problem, the issue is that whenever your pixel is predicted above 50, it's usually considered as a 1, below is considered as a 0, or you use this rule of the true skill statistic maximization. But this optimum shifts. So if you use this calibration, as you can see in this bar plot here, you see that the threshold of which you put the cutoff for your probability maps changes drastically. For example, in this case, for the common species, you actually have a higher threshold, while instead for the rarest species, the threshold is much lower. So this is not a really good rule to select where a pixel is suitable versus unsuitable. We created, we decided on an heuristic where this threshold gets selected based on a precision equal to recall for the common species. And for the rare species, we decided to use the F2 score, so to reward the model more for the recall rather than the precision. In this case, we try to get more, to predict the positives much better than, and then having a little bit more of false positives rather than avoiding having suitable areas not included in your final map. And this is what you can see in this selection of the threshold, in this case for the chestnut. On the left, you see using just raw probabilities and this true skill statistics maximization, you see that the area of the chestnut is quite spread in current condition, while the model is a bit, as I said, worse than before. While instead, if you use these calibrated probabilities plus the threshold used for the F2 score, which, yeah, you cannot see it, but for the for basically the raw map, it's the threshold is like 0.13, and in this case, for the calibrated is 0.18, so it's a bit higher. It might be not that interesting here in current condition, but you can see already now that with the current area of the species, if you make the difference between this calibrated map and the raw probabilities, there are a lot of areas that are false positives where this species is actually not present. And as I said, this may not matter much now, but if you go up to 2100 for the RCP 8.5, you have a considerably over prediction of the area of the range of the species. So if you consider the log likelihood of these probabilities in this specific scenario, if you use just the raw probabilities and the threshold, you overestimate up to 2.5 times the actual area that the species could cover. So it's extremely overconfident, and it can lead to wrong decisions. So the next step in this case is that we have all the models already ready. We just need to finish all the maps and clip possibly with some land cover masks, so to have an idea of where the forests are and where they're not. Calculate area gain and losses, because there are so many papers and products that do a similar thing with 3 species ranges. But since they do what I shown before with the raw probabilities, most of the areas that are considered suitable are extremely overestimated. And yeah, define which species are considered as winners and losers. So which areas would gain more range with climate change. And then define a proper uncertainty metric, because in this case, we could have just gone with the standard deviation of the base learners, but we can also go to conformal prediction or other type of calibration techniques. And finally, we have to, of course, prepare a draft with publication manuscript, publish data on Zenodo, Stack, and so on, and ultimately integrate that in the OMC front end. So this is it. I think we may be a bit heavy, statistically speaking, but thank you for listening.
Okay, thank you. Let's see if there's questions for Carmelo. Yes, here's a question.
Yes.
Yeah, so interesting talk. But I was curious, how many of the trees are or have been planted, let's say, and in that way influence the model? Like they're not really that suitable, but historically they have been planted and are kind of part of your data.
And no, they're already included. So it's not just the natural range of the species, but includes also trees that have been planted outside of their own native range. So we consider as native range the historical climatic period that we started from the 80s until the early 2000s. And if the species is considered suitable in that historical period, that's considered as the baseline for where the species could be suitable.
Okay.
More questions? Why 250 meter? Why not higher resolution? Is it some reason because of the spatial accuracy of plots?
Yeah, it's because of the plots, because we
Okay.
have buffered coordinates. So
Okay.
if we use a higher resolution, then you risk getting.
But if you had a better resolution, then you could have done it on.
Yeah, exactly. The only thing is that you would match the elevation or the topography, but from a climatic perspective, you cannot make the maps.
And what's the most important covariates for this species?
I haven't tested that.
Different.
Yeah, because basically you having a stacked model, that means that you would have to calculate the variable importance for all 5 base models, and then you would have to scale them up based on the importance in the final model. So it's a bit.
Okay. Okay, looking forward to the paper. Thank you, Carmelo. We continue. We have a little change in the program. Gilberto Camara is presenting in the afternoon. In the